Okay, guys, I'm going to show you a short clip here from the Mechanical Universe episode on waves. I'm going to have you watch the entire episode a little bit later on. First of all, I want to cover some of the basics of the physics of water waves. So I have the film frozen right here at this moment where they're going to talk about the speed of a water wave in deep water. That is, where the wave itself does not interact with the ocean bottom. Okay, deriving this expression by using fluid mechanics is quite difficult to do, but the gist of it is that the speed of a wave in deep water is proportional to the square root of the wavelength. So if you increase the wavelength, this then means that the speed of the wave increases. If you decrease the wavelength, this then means that the speed decreases. So then therefore small tiny ripples then propagate along the surface of water at a speed that is less than the speed of ocean swells, which for example have a larger wavelength. Let me go ahead and set this into motion such that I could show some animation associated with that. Okay, the sound here is turned off in the film. Okay, so there are some long wavelength ocean swells, for example. There are some tiny ripples of a smaller wavelength, and notice how much more slowly they're moving. So if you combine the two together, then you end up with this type of a waveform. That is what happens if you have a wave in deep water. I'm just going to let the film scroll forwards here a few more minutes. What they're going to depict next is that water waves, in fact, are actually neither longitudinal nor transverse. So first of all, here in the film, they're distinguishing between longitudinal and transverse. That's first of all longitudinal like so. And then secondly, transverse like this. I don't quite know what the hairy foot means, but oh well. Okay, and now what they're going to do is they're going to show us here the surface of water. The surface of water is actually neither transverse nor longitudinal. Instead, it looks like the following. Like so. So each little bit of water at the surface actually moves in a tiny circle as the wave propagates, resulting in this familiar undulation associated with water waves. Okay, next they're going to cover here briefly what happens when a water wave does interact with the seabed below. This then means that the wave slows down and it rears up because kinetic energy is being converted into potential energy. But the speed of a water wave when it interacts with the ocean bed below is dependent upon the square root of the depth. That's the h that you see there in the expression. So as waves approach the shore, they slow down. This then means that the top of the wave is moving more quickly than the bottom of the wave, and then therefore the wave breaks. So here's then what happens as the wave approaches the shore. Top of the wave is moving more quickly than the bottom of the wave because the water is deeper at the top of the wave than it is at the bottom of the wave. And then ultimately the wave breaks like so. Okay. All right, I'm going to go ahead and pause the film here. There's a nice black sand beach. As I said a little bit later on, I'm going to have you then go